Welcome back. Let's talk a little bit now about quantifying and measuring thermal energy. So last video we talked a little about what energy is, how it can be classified as kinetic or potential. We're going to talk about energy being transferred now and we're going to talk about how we quantify that a little bit. So when we're talking about thermal energy, we're talking about the energy associated with the random movement of particles. So something that's hot has particles that move a lot faster than something that has cooler particles. And when we heat something, right, we raise the temperature of it, and the amount of heat we add to it is proportional to the temperature rise and can be related by an equation. That's the equation we're going to work with here. We're going to have a couple new units. The first is a joule, which is a unit of energy, and the second is a calorie, which is another unit for energy. And calorie can be related to joule. 4.184 joules are equal to a calorie. Note that little c calorie here is bigger than a big c calorie, like on your food. A big c calorie on your food is actually a kilocalorie, or 1,000 of these little c calories. We might have to do a little bit of conversion, so I'm going to introduce a little bit of dimensional analysis here, which shows how we convert between units. So for example, if I have a question like this, how many joules are in 85.4 calories? What you're going to do, you're going to put what you start with, which is 85.4 calories, and you're going to multiply it times a fraction. And the way you kind of set this up is whatever we're trying to convert out of goes down here, and whatever we're trying to convert into goes up here. And we're going to go into this in a lot more detail in a later chapter. I just want to introduce it a little bit here. We'll see it a little bit in the lab. But 85.4 calories, so what we can do is we multiply by, there's 4.18 joules in a calorie, so we multiply by that and then we get our answer and round to the correct number, sig figs. And the advantage of dimensional analysis is that what we're really doing here is we're multiplying by a fraction that's equal to 1. Right? This in this box here, this is equal to 1 because the numerator here is equal to the denominator. And what happens when we multiply this way, these units cancel, and we're left with the unit we want, which is joules. Okay, so here's a couple other examples with that. You might see this. I'm not in our regular chemistry, I'm not holding us accountable to do this just yet, but I wanted to just introduce it here so that you can see a little bit about how it works, because we will see it in some labs coming up. What we do want to be able to do is use a new equation. So our equation for measuring heat is Q equals mc delta T, where Q is the amount of heat, which can be measured in joules or calories, but we're going to use joules for now. M is the mass of the substance, which we measure in grams. C is a constant called the specific heat of the substance. And delta T, delta means change, is the change in temperature. So this is the final temperature minus the initial temperature. And we're going to use this equation whenever we're talking about a substance absorbing or releasing heat. And the simplest substance to think about is water, and that's going to be the one we use the most. All right, so what is specific heat? Okay, specific heat has to do with the material we're using. So if you think about a day at the beach, right, at the beach there's water and sand, and there's Mr. Golden sun shining down on the beach, right? But that sand gets a lot hotter than the water does on that day. Why? Well, sand has a much lower, you can think of sand like concrete or asphalt. Or no, oh, right here, sand. Okay, sand has a much lower specific heat than water, which means as the sun is beating down on the beach, right, the sand to go up 1 temperature only needs to absorb about 1 joule of energy. Where the water, a gram of water to go up 1 degree needs to absorb about 4 joules of energy, so almost 4 times as much. Okay, so we're going to use the specific heat, it's C in the equation, and for water it's 4.18 joules per gram times Kelvin, which I'll talk about what all that means. But for now, that's a little bit of an intro of what specific heat is, and it's different for each substance. It's the amount of energy required to raise 1 gram of that substance by 1 degree. It's also what we call a constant, which means anytime we have water, when we're using our Q equals mc delta T equation, you're going to plug 4.18 joules per grams times degree C in for C. Okay. All right, so what about the delta T? Q, we've used variables before. We've used Q is going to be heat, M is going to be mass. What about this delta T? Well, delta means finest my initial. You can think about slope from math class, right? The change in y over the change in x, or your final y minus your initial y gives you your delta y, right? Delta T is the same thing. Delta T is going to be the final temperature minus the initial temperature. So you got to read the problem carefully. You write your general equation, you substitute in, and you solve for your answer. Now, if you want, you can pause here and try the other two. Okay. Note that we want to keep careful track of the sign. The sign is going to give us some information that the temperature decreased. Okay. And that sign will carry over to Q, and that'll tell us some information about whether energy was absorbed or released in the problem you're looking at. Now, this will be part of a larger problem. So let's take a look at a full heat example. A 425 gram sample of water increases in temperature by 15 degrees. How much heat was absorbed by the water? So I've given you the mass. I've given you the delta T because I've told you what the temperature change was. And you also know C is a constant. So you write your equation. You substitute in. Notice I've included all my units here, and my units do cancel, right? I have grams on top here and grams on the bottom. I have degrees C on the bottom of this fraction and on the top here, and I'm left with joules. So then I get my answer, punch in my calculator, round to the correct number of significant figures. I opted to use scientific notation here. 2.66 times 10 to the 4th joules. The best way to do this is to do some practice. Here's another example for you. This time we have ethanol, so notice that we have a different specific heat given to us. So instead of 4.18, we're going to use 2.44 with these units. Here you also have to calculate the delta T. Read the problem carefully to know what the final temperature is versus the initial temperature. It's not always the bigger number minus the smaller number. Down here, I use Q equals MC delta T. I plug in my values, keeping track of all my units. If I want, I can show how the units cancel. This might be a little bit uncomfortable for you at first, but in the long run, helps you see that you've done the problem correctly. I then give my final answer, and to make it clear that it was 3 sig figs, I decided to show it in scientific notation. Here's one more. 2 more with those examples for you. This last one here I like because you have to solve for the missing variable. So you treat the procedure the same, but then you have to do the algebra to solve for M there. And that's a little bit on how we use the Q equals MC delta T. You're going to want to find some practice to do to make sure that you really know how to do this, and perhaps resort back to the video if you want a few other tips. Good luck.